But then you go crazy and totally yeah, I think my life might be worth I think it was worth the next that's how I think so, it'll probably just be like me and whoever else with the website and I think it's what about you? He was trying to get me hyped on the Smith trip.
Yeah, that would be fun.
I think you know would be more. It's not going anywhere. Like this particular experience, if you know, is
Yeah.
All right, I hope you all had a good weekend. You probably saw the grades got posted at some point last night for the midterm. So in general, the midterm was done not so bad, actually. I was a little stressed out, like when the midterm was happening, everyone was here right till the end. But so you surprised me. It was pretty well done in most cases. So thanks. I hope you feel good about that. The distribution was a little bit bimodal. So if you plotted the, oh, you can see that well. If you plotted the distribution, it would look something like this. So these are the grades, and this is the distribution. It was something like this. And so you hopefully want to be in that group, right? Thank you. So okay, we've got our assignment 3s graded. Thank you very much. So I'll return those at the end of class. So where this peak is like somewhere around 70 to 75 range, and then this one is maybe closer to like somewhere in the kind of 55 to 60 sort of range. So just so you know, that's so you know where you're standing. That's how it looked. So the other thing on the midterm, some of you may have noticed that there was that one question where you had to evaluate an integral using a delta function. Unfortunately, I used delta inside an exponential, which was weird. So what I've done is, because that was my mistake, and it could legitimately confuse people, everybody got 3 out of 3 on that question, regardless of what you wrote down. But even though I made that mistake, most of the class got most of those marks anyways, okay? And then finally, last comment about the midterm is that I will post my solutions. The reason I haven't posted them yet is because we had 2 students still who have yet to write the midterm. They've now completed the midterm as of today. And so my solutions will go on the course website this evening sometime. Okay, and then I said assignment 3, in fact, this is assignment 2 graded. Assignment 3 is now available on the course website. It is about separation of variables, but you're going to derive what you would do for separation of variables in cylindrical coordinates for the case where there's no dependence on the z axis or the z direction. So any questions before we get started? All right, so let's just recap what we did last time. We kind of finished the problem, but we didn't write down a nice final solution. So let me just remind you of what we were working on. We were doing separation of variables in spherical coordinates for the case where the potential was expected to have azimuthal symmetry. So had no dependence on the phi coordinate. We found that in general, we could write the potential in this way. Oops. And so there it is. And then from that point, what we had to do is we had to specify some boundary conditions. So what we considered was a hollow sphere. So this is a spherical shell, and we imagine that somehow the outside of that shell is held at some potential given by sine squared over k times sine squared of beta by 2. So the first part of the solution was to recognize that I could write sine squared as 1/2 times 1 minus cos of 2 cos of theta. But then I could write the 1 and the cos theta in terms of Legendre polynomials, the first and the second one, which are P0 and P1, so that we could then say that this potential is just equal to some difference of Legendre polynomials, essentially. And then we went through and we started applying boundary conditions, and we found that the general solution is only going to involve L equals 0 and 1. And so we had to find those coefficients. We found A0 and A1, and we also showed that BL had to be 0 for all possible L values, so that we could finally then write down that the potential inside the spherical shell is given by this expression. Okay, so that kind of wraps up chapter 3. We're going to jump ahead to chapter 5, which is going to start involving magnetic fields. Chapter 4, which we're skipping for now, considers electric fields inside of materials. And what I hope we'll be able to do is come back and pick up some topics from that chapter closer to the end of term. I just want to make sure that we have lots of time to cover magnetic properties or the magnetism in electromagnetism. Okay, so thank you. Let's go. So far, we have limited our discussion or analysis to the case where the source charges are at rest, so they're stationary, to the case of stationary source charges. Okay, and we found that those stationary source charges produce static electric fields. Okay, and so that whole field we might call electrostatics. So what we want to do is we want to now relax that constraint and allow for the possibility that we have moving charges. So a moving charge or a current can interact with moving charges or currents can interact with one another in a way that does not rely on electric fields. Okay, and so what I'm going to do, or say Coulomb's law. Coulomb's law said that the force between two point charges was proportional to the product of the charges divided by the square of the distance between them. So to try to convince you that this is possible, what I'm going to first do is show a little video of a demonstration. This is a video from MIT. It's short, it's less than a minute. And I'll let it run a little bit. We won't bother with the audio. I'll give you my commentary. All right, so what they've set up are two parallel wires, and then they have a battery. It's a large battery, it's like from a car. And they've got this little switch device, and what they can do is they can send the current up, let's say the right wire, and then back down the left wire. And so in that case, the currents would be anti-parallel. And if they put the switch in the other position, what it does is it puts the currents in the same direction, so parallel. And we just want to see what happens when you have large parallel or anti-parallel currents. So parallel switch backwards. I guess he's going to do it now. I assume. So anyways, that's the parallel currents. They repel, and then anti-parallel attract. Or maybe it's vice versa. We're going to do the analysis. So here we go. That's anti-parallel currents. They repel, parallel currents attract. And so why does this have to be the case of not an electric type interaction? If you think of these wires, I mean, it's almost 100%, it's copper wire inside some insulation. And in copper, what you have are a bunch of fixed ions, so positive cores of protons and neutrons surrounded by electron shells. There are inner electron shells. Those electrons are stuck to their host atom. And then there's electrons in the valence, or the outer shell, and those can easily detach from their host atom, and they can move around throughout the conductor. So what that leaves you with are some fixed positive ions, and then some mobile electron negative charge that can move around. When you start a current going, you're taking some of the mobile electrons, and maybe they're leaving the top of the wire, but at the same time, more electrons are injected to the bottom. And so that means you always have a wire that's electrically neutral. It's just that the negative charges are flowing. If these two wires are always neutral, then the repulsion or attraction can't be due to like a charge effect, or the effect of the electric fields due to some conductor that has a non-zero net charge. So that's impossible. And so it must be that somehow the motion of the charge is responsible for this interaction. Okay, so I'm just going to write some comments about that little demo that we saw. Let's consider some parallel currents. All right, so we'll have one wire with current I1, and then beside it, we'll put a second wire that has a current I2, like so. All right, and what we observe is that the force let's say the force of 2 on 1 is to the right, and the force of 1 on 2 is to the left, and so this would be an attraction. Why would it be necessary that if this one attracts this one, the wire on the left, what law do we know that would say it must be the case that the wire on the left attracts the one on the right? Newton's third law, right? That's equal and opposite action-reaction type force pairs. Okay, so let's not pretend like we don't know something about this. What's going on? Why are these attracted to one another when there's no electric fields involved? Yeah, exactly. So we know that moving charges or currents are a source of magnetic fields.
Is that a conservation law? Like, isn't that conservation of magnetic flux?
I don't think so. I think this is, I mean, if you read the textbook, then what Griffiths says is what we're going to write down does not come from any kind of fundamental derivation. It comes from experiment. So all of E&M, the whole theory rests upon what he calls an axiom, which is going to be the Lorentz force law that we're going to write down in a few minutes. And so there's no first principles derivation of this. It's all based on experimental observation. And no. So that's, we observe this, we write down that law, and all of E&M is what are the consequences of this force, this interaction between these charges. Okay, so let me emphasize that moving charges or currents are a source of magnetic field. So if you remember, the way that you would find the magnetic field is you would take this wire and you grab it with your right hand in such a way that your thumb is in the direction of the current and your fingers curl around in the direction of the magnetic field due to that current. So if I do that, then the field due to this current at the position of this wire is into the screen. And so we're going to have a magnetic field due to 1 at the position of I2 that's into the screen. And likewise, if I do it for I2, I grab this wire with my thumb pointing up, then out here, the field's pointing out of the screen. And so this is the magnetic field due to current 2 at the position of current 1. So this would be B2. Okay. What we'll end up writing down is a force on this current or these moving charges due to this magnetic field. And that's going to be the source of the attraction and repulsion between the two. If you think about it in this way, like charge is kind of this amazing thing, right? Not only is a charge a source of all electric fields, it's also the source of our magnetic fields. It just has to be moving. So this one object gives rise to all of the charges, give rise to all of the E&M type phenomenon that we see. Okay. Yeah.
I remember from like first year.
Yeah.
Is the fact that a magnetic field came from an accelerating charge. Does it matter whether it's accelerating or just moving at a constant velocity?
No, moving at a constant velocity. We're not going to do it, but when you do 401, you'll consider accelerating charges. And what they do is they're going to read. Yeah. Okay. So the kind of simple picture is that I1 creates a magnetic field B1 at the position of I2, and then B1 exerts a force on I2 that in this case acts to the left. We'll write down an expression for that force today. Let me just make sure I got it in the right direction. Yeah, that's right. Okay, good. Okay, so likewise, we could say that I2 creates magnetic field B2 at the position of I1, and we get an equal but opposite force on I1. Okay. So let's just note that at all times, both wires are electrically neutral. So the force is not due to electric fields or Coulomb's law or something like that. It is the motion of charge that creates magnetic fields that facilitate the interaction. Facilitate the interaction. Okay. There's another way that we could see, I mean, this first little demonstration was to try to show that the motion of charge gives rise to this kind of new interaction. It's pretty easy to see that currents are a source of magnetic fields, and you can do that just with a wire, a battery, and a little compass. So a compass can be used to confirm that moving charge is a source of magnetic fields. Okay, so let's imagine that we have this wire that has a current. So I'm not going to draw it, but you know, we imagine that there's some smaller wires coming off of this that go to a battery, and that battery drives the current. And then what I do is I take a little compass, I put it next to this wire, and I find that when the current is off, the compass needle points north like normal due to Earth's magnetic field. But then when I turn the current on, that the compass needle is deflected. Like there's a famous story of, was it Faraday who was doing a demonstration? I don't know who it was. Someone was doing a demonstration in front of a classroom or an audience, and they turned the current on in a wire and they saw the compass needle deflect. And so that was the revelation that led to this sort of connection between electricity and magnetism. And then what I do is I just take that compass and I move it to different points around this wire. And what we find is that if I connect these, that they kind of form this loop that goes around the current. And so there's our magnetic field. Now, if you could, like, you know, what this magnetic field is doing is putting a little torque on the compass needle. If you could measure that torque somehow, like you get a really sensitive device, measures how much that field twists this needle, as you move the compass further and further away, that torque would get smaller and smaller. So the field gets weaker as you move away from this current. Okay, so magnetic fields form closed loops around moving charges or currents. Okay, you could do sort of an analogous thing with not a current, which is like a flow of, say, Avogadro's number of charges, but you could take a single point charge and you could say, all right, let's take point charge Q and let's make it move with some velocity V. And I'm going to do the same trick with the compass. In principle, I could anyways. And what I would find is that close to the charge, we're going to have these magnetic fields that loop around, and I'll draw a few more lines. And what I'm going to do is I'm going to try to space them out further and further as we move away from this charge, indicating that the field is getting weaker as we move away. And if I extend this line, so maybe this charge is going to follow this path here. I could also take a compass and stick it over here while the charge is at this position, and I'll detect a magnetic field. It'll just be weaker. So if the first field line is like this, the next one will be further away. And so I could say this is weak magnetic field, and this is strong magnetic field. And in fact, I could even place a compass behind this moving charge, and what we would see is we would get another weak magnetic field back here. So weak. So we can already see that these magnetic phenomena are going to be a little strange, right? When we had electric fields, they always started on a positive charge and ended on a negative charge. So they had these two endpoints. They didn't form these types of loops that we're drawing here. So that's already different. Electric fields tended to point radially away from charges. Magnetic fields loop around moving charges. And so there's lots of peculiar things, and it's going to lead to peculiar effects. And we'll see one of them today. Yeah.
Would you say, like, if you could see all of the field lines around a moving charge, would it be more of a bubble, or would it be like related to the
I mean,
direction?
so it would be like if you wanted to plot like the strength of the field, it would be weak here, and then it would get strong, and then it would get weak. So maybe that's what you mean by like a bubble.
Yeah.
But the field lines are everywhere, all throughout all space. It's just that they're really far spaced apart over here, and they're more dense over here. Yeah, yeah. But the strength is definitely the biggest next to the charge. Yeah. Okay. So let's just write down a right-hand rule for B due to a current. And so what you're going to do is you're going to imagine that you grab the current carrying wire with your right hand such that your thumb is in the direction of B. And if you do that, your fingers curl in the direction of the magnetic field. Okay, and so let's see how that would work here. For the current in the top, if I'm going to grab that wire, I can grab it in two ways. I can grab it like this, or I can grab it like this. And what I want is my thumb to be in the direction of the current. It has to be a right hand, and my fingers loop around in this direction. So if I look from above, it would be a counterclockwise rotation in this case. It doesn't have to be the current. Like if I put my thumb in the direction of the velocity of this, say, positive charge, then my fingers would curl in the direction of the field. If this charge happened to be negative, then you would do right-hand rule. It's just that the field that you would get would be opposite the direction of your fingers. Okay, good. So the other thing you can do is you can also use something like a cloud chamber to confirm that moving charges experience a force due to magnetic fields. So what is a cloud chamber? A cloud chamber, you, roughly speaking, you take some dry ice at the bottom, so it makes a cold environment, and then you have like a piece of felt that you've soaked in alcohol or something like that. That makes a vapor of alcohol that's above the cold, dry ice, and it turns out you can make a saturated vapor, so that if anything passes through that saturated vapor, it causes a little trail of condensed bubbles, condensed liquid, and you can see the path that these particles that fly through this vapor follow. So we get lots of charged particles flying through us all the time. One source is from the sun. So the sun makes the solar wind that emits these charged particles, and they eventually, some of them arrive at the surface of the earth. So if we have our cloud chamber sitting there, we just sit there and watch it. And once in a while, you'll see a little trail of these condensed vapor particles that tell you the path followed by one of these charges from the solar wind. And what you could do is you could take a strong magnet, you put it next to your cloud chamber, and now the lines that were initially straight will start to be deflected. And so that's the magnetic force on a moving charge. And so what that might look like is, let's imagine this is the wall of our cloud chamber. So our cloud chamber is on this side. And over here, we have just free space. And so suppose that we had a charged particle come in. Initially, I wouldn't see it as it moves through free space. So let's say that's positive charge and it moves in with some velocity. But then when it enters the cloud chamber, it would follow some path, and we'd see that path from the vapor trail that it leaves. But now we're going to do one other thing. Let's turn on a magnetic field. So we'll have a magnetic field pointing out of the screen, for example. Let's see if this is a positive. All right, so it'll be deflected down. So now we're going to have this vapor trail, and it's going to show a curved path. Vapor trail is curved due to the magnetic force. All right. So the summary is that charges produce both electric and magnetic fields. However, you only get the magnetic fields when the charges are moving. Okay, so let's write down this fundamental law. If one was to experimentally investigate the force on a moving charge due to a magnetic field B, some of the things that you would discover would be the following. So they would find some a little bit surprising or unusual properties. And so let's write some of them down. Some of them are unusual, some of them aren't. So one thing you would find is that the force, the magnitude of the force, would be proportional to the charge Q. And so that's not so surprising. You could say that about the electric force as well. Yep.
Question.
Yep.
The magnetic field is created by the moving charge because the charge now is in the x, and in the few seconds it is the x plus some integer. I mean, but if we have the infinite number of the charge, so we can assume that they are not moving because, for example, when one charge is moving, because of the changing in the place, the magnetic field. But if we have the infinite number of the charge, they are identical everywhere. So
Yeah, it's still, so you would still get a magnetic field. Like, imagine a wire, and so you could have like a very high density of charges, and they're all moving together. And you could say, well, at one time I see a certain amount of charge, and another time I see the same amount of charge. So why is that different? So what you would do in that case, you would say each individual charge that's moving creates its own magnetic field. And the total field that we get would be the superposition of the fields due to all those individual moving charges. So you would still see, if there's moving charge, you would get a magnetic field. Yeah. So, so some of the other properties that you would see is that the force would be proportional to how fast the charge is moving. And so maybe that's not that unusual either. You could probably be convinced that that's not so strange. And then maybe that the force is proportional to the magnetic field strength is also not so surprising. And so these are not really unusual. But then we get some weird ones. The first weird one is that the force is proportional to the sine of this angle theta. And I'm going to draw a picture so that we can see what theta is. Okay, and so I'll draw my picture over here. So let's imagine that we have this dashed line, and we're going to have some moving charge that's going to follow this dashed line path. Or at least it's on a trajectory that, in the absence of any forces, it would follow this path. All right, and then we're going to turn on a magnetic field. And we turn on this magnetic field, B. And so I'm just picked an arbitrary direction. The angle theta that I'm talking about is this angle between the velocity and the magnetic field. So it's this weird thing where here in theta is 90 degrees, sine of theta would be 1. That's where the force would be a maximum. So if the magnetic field is perpendicular to the velocity, you get the maximum possible force. If the magnetic field is parallel to the velocity, you get sine of 0, which is 0, and you get 0 force. So it's only the component of the velocity that's perpendicular to the field that is responsible for the force that we see on it. So if theta is pi by 2, F is a maximum. I guess we could say plus or minus pi by 2 if we wanted to. And if theta is equal to 0 or pi, F is 0. And then you get all the intermediate values between those two extremes. Okay. The other unusual thing is that the force, I'll draw it as a vector now. The first 4 have been concerned just with the strength of the force. The direction is perpendicular to both V and B. This is the part that I think is really makes the magnetic force kind of different than some of the other forces that we're familiar with. Think of the electric force. F is Q times E, so the force is just in the direction of the electric field. Think of gravitational force. Near the surface of the Earth, it's just m times g, so the gravitational accelerate. The force is just in the direction of the field. Here, we're going to get a force that is perpendicular to V and B. And it would turn out that in this case, the force would be out of the screen. Whoops. screen. Okay, all right. So all of these observations can be summarized as follows. The magnetic force is equal to Q V cross B, and this is the Lorentz, Lorentz force law. All right, and this also tells you how to find the direction of the force, right? I have two directions for the force that are both perpendicular to V and B, and so you have to use the right-hand rule for cross products. Let me just remind you of what it is. You put the way I do it is you put your right arm in the direction of the first vector in the cross product. In our case, it's the velocity that's off to the right. And then I'm going to curl my fingers so that they are parallel to B. And so B is kind of sloping up this way. And so I'm going to make my fingers parallel to B. My thumb points out of the screen. That's the direction of a force. And that's the green dot there, the arrowhead coming out towards us. Okay. So what if you had a situation where you had both an electric field and a magnetic field? So if there are both electric and magnetic fields in the region of space through which a charge moves, then the total force will be the sum of the electric force, which would be Q times E, plus the magnetic force, which would be Q times V cross B. And this is the one where, if you read Griffiths, he calls this an axiom of electrodynamics. And what we're trying to do is work out the consequences of this Lorentz force law with the electric force included. Yeah.
So if the particle's not moving, then it doesn't interact with the magnetic field either.
Yeah, that's right. So like it's even more than that. If it's moving and it happens to be moving parallel to the magnetic field, it wouldn't feel any force on it. Yeah. Yeah. All right, good. So let's work out some consequences of the Lorentz force law. Some of them you will have seen, and maybe one you may not have seen before. So let's start this on a new page. Consequences of the Lorentz force law. I'm going to restart this tablet to see if I can get it to, sorry, not the tablet. I'm going to restart just that software and see if I can get it to write more smoothly. Okay. Yes. Okay. So one. Oh, that's much better. So let's imagine Q moving through a uniform magnetic field. And we're going to be even more restrictive than that. We're going to force the velocity to be perpendicular to the magnetic field. Okay. So let's take a magnetic field that's uniform. That just means it's constant in some region of space. We'll draw it as if it's coming out of the screen, like so. And then I'm going to take my charge. I'll take a positive charge, and let's suppose that it's moving at this moment with some velocity v. So there's v perpendicular to the magnetic field, v, right? Okay, and we'll say that this is a q that's positive. All right. So there's no electric field, so there's no electric force. What we have to do is we have to work out the direction of the magnetic force. What do we have to do? V cross B. V, and then curl my fingers in the direction of B. The force is downwards. All right. So say, all right, that's fine. So we have a magnetic force that points down. Well, if the magnetic force is pointing downwards, then that's going to deflect the charge. And so it's going to follow some kind of path like so. What's happening to the speed how do the speeds compare at this point and this point? The speed, the same. When we have a force that is perpendicular to the velocity, the speed cannot change. The charge is still accelerating, but the acceleration is entirely due to changes in direction of the velocity. So since the magnetic force is perpendicular to the velocity, the speed of the charge doesn't change. Only its direction, its direction of motion changes. All right. Well, that's interesting. If the speed doesn't change, what about the kinetic energy? Does the kinetic energy change? No. Okay. So therefore, the kinetic energy, which is 1/2 mv squared, is constant. All right. Well, what does that mean? The work kinetic energy theorem. So let's apply the work kinetic energy theorem to the magnetic force. The work kinetic energy theorem says that this integral, this line integral from some point A to some other point B is equal to the change in kinetic energy. What's the change in kinetic energy? Zero. So this line integral evaluates the work. And so magnetic forces do no work. So the magnetic force on Q does 0 work. Okay, so that's interesting. All right, so let's go back to this picture. So we've let our charge move a certain to some new position. We've already concluded that the speed's not changing, so this red arrow should always have the same length, only its direction is changing. And so we say, okay, well, what's the force now? Well, okay, V is down across B. Oh, okay, the force is towards the window. And so that looks something like this. And so now the charge is going to be deflected to the left. And so it follows this path, comes over here. Now it's moving with this velocity. If we did the right-hand rule, the force would be in. That would deflect the charge upwards. And it comes over here. Now it's moving in this direction. The force would be to the right. And we would get back to our starting point. And we would move in this circle of some radius r. So a charge moving perpendicular to a uniform magnetic field undergoes circular motion. Okay, so that's kind of a qualitative sort of analysis. Let's see if we could work out some of the details. All right, magnetic force is going to be QV cross B. So if I wanted to say the magnitude of this force, that would be Q times the magnitude of V cross B. What's the magnitude of V cross B? Yeah, it's VB sine theta. So it's like the dot product. The dot product would be, if it was V dot B, it would be VB cos. So for magnitudes and cross products, you get the sine. But for perpendicular vectors, what is the angle here? 90 degrees. So this is going to be equal to 1 since theta is pi by 2. All right, so the magnitude of our force, and I'll indicate the magnitude just by leaving a vector sign. Actually, one comment about the midterms is some people are a little bit lackadaisical about vector notation. I was a little generous for the midterm, but I want you to make sure you're handling the vector notation properly. So this without a little arrow on top is going to mean the magnitude. I will treat those as a scalar from now on when I mark your work. Okay, good. All right. So fair enough. What else do we know about something that goes around in a circle? What do we know about its acceleration? Yeah, it's the centripetal acceleration. So the force on an, let's say the net force on an object in circular motion is, I don't know, F is equal to M times the centripetal acceleration, which is V squared over R. And so for our problem, we have only a magnetic force acting on our charge. And so therefore we have mv squared over r is equal to qvb. You can cancel one factor of v. And we can solve for the radius, for example. R is going to be what? mv over qb. So this is the radius of the circular motion. All right. Let's go ahead and let's think about how long would it take our charge to complete one loop. We'll call that the period of the motion, right? Because if we just let this go, it'll just keep tracing out the same circular path over and over and over again. But let's say that we want to find the time for one loop. So the charge has to travel a distance of 2 pi times r, the circumference of the circle. And we know it's always going at the same speed, v. So we should be able to find the time. So the time it takes to complete one loop is, let's say the time it takes to complete one loop, which we'll call the period t, is, t is 2 pi r, the total distance it has to travel, divide by its constant speed. Oh, okay, well, that's just 2 pi over v times the radius that we just calculated, q over v. That's kind of interesting. The v's cancel. And so this period is equal to 2 pi m q over v. Usually the way you'll see this expressed is as the so-called cyclotron frequency. Omega c is 2 pi over t. So 2 pi divided by t would be qb over m. this is the so-called cyclotron frequency. The reason why this is maybe a little interesting to us is that we live not so far away from the cyclotron. There's one at the Vancouver campus of UBC. It's called Triumph. So Triumph, they spell it a bit funny because it's something like Tri-University Maison Facility is what it stands for. But the interesting thing about this is that this frequency, or in fact the period, doesn't depend on how fast the charge is moving. So that's kind of a cute result. The reason it doesn't depend on how fast it's moving is because as you increase the radius, the speed increases by the same factor. So you increase the radius, the particle has to move farther, but it moves around at faster speed. And so the time to complete one cycle is always the same. And this fact is really important for how cyclotrons are built and operate. I won't go into the details, but they start with a charge moving slow with a small radius, and they accelerate it, and it moves out to a bigger and bigger radius, but it's always taking the same amount of time to complete a loop. Okay, anyways, before we move on, there is one other interesting fact that we should just point out, just because it's an important application. If I look at this picture here, I can easily make a uniform magnetic field. One way to do that would be by using a solenoid or something, but there's other ways we can make uniform magnetic. So this is possible to make. So let's suppose we discover a new particle, brand new particle. It's very exciting, right? We're pumped up about it. We want to work out some of its properties. And so what we're going to do is we're going to fire that particle with some velocity into this magnetic field. If our particle is not charged, nothing's going to happen. So before it gets into this magnetic field, we're going to ionize it. We're going to maybe shoot some electrons at it or something. We're going to either add an electron or knock one off. So now we have a charged particle moving at some known velocity in a uniform magnetic field that we set up. And it's going to move around in a circle. And if we could measure the radius of that circular motion, then we could go back here and say, okay, I'm going to measure the radius. I know that. I'm the one who fired the particles into the magnetic field, so I know how fast they're going. I'm the one who set up the magnetic field, so I know how strong the field is. I ionized my particle, so I know it has a charge of, say, I don't know, minus E or something like that, or plus E. And so now the only thing that's not known here is the mass. And this is 100% the basis of mass spectrometers that are used all the time. Okay, and so the physics is fairly, I don't know, understandable. Okay, this is the kind of problem that we would give in our first year class. Okay, so let's move on. What I hope to do, what are we supposed to do? We're supposed to go for, yeah. Maybe I'll do one more thing here. I have a little demo set up where we could actually see charged particles moving in a circle, and we can tune magnetic fields and see what happens to the radius. So I want to do that. So let's spend 5 minutes doing this next thing, and then we're going to go to a lab in the science building and we'll look at this demo. So if the particles motion has components that are perpendicular and parallel to B, then the parallel component of the velocity is unaffected by B, because it's only the perpendicular component that results in a force. So let's suppose we had some magnetic field B. I'm imagining that we have this uniform magnetic field that fills the space, but I'm only gonna draw one of the lines, okay? Just this, a uniform magnetic field. And we're gonna take our charged particle Q, greater than 0 maybe, and we're gonna give it some velocity V, but we're gonna say that velocity is not perpendicular to the magnetic field. It will have a component that is perpendicular, but it'll also have a component that is parallel. So let's see, if we take the perpendicular component cross B, the force would initially be out of the screen. And so what we would see is this thing would follow some kind of path that would begin to circle around this magnetic field line. But at the same time, it's not accelerating along this direction, so it just keeps moving with a constant speed along this direction, and our circular motion becomes a spiral path, like so. I can't draw it perfectly, but it's something like that. So the particle spirals around the magnetic field. So I have some pictures here. This is also relevant, if I can find the right one. Yes. So anyways, these are just the notes that I was preparing last night. So here's Earth. We were already talking about the solar wind, how it blows these charged particles towards the Earth. And Earth has its own magnetic field, and so here's the magnetic field lines. Charged particles that get close to the pole of the Earth, north or south, in fact, will spiral around that magnetic field line. So this motion is due to the component that is parallel to the magnetic field, and the circular part is due to the component that is perpendicular. These charges are guided towards the pole of the Earth, where there is some atmosphere. They are moving at high speeds, they have lots of energy, they collide with particles in that atmosphere, they excite those particles. When they de-excite, light is emitted, photons are emitted. Some of those are in the visible range, and you get the aurora borealis of the northern lights.
Does it
Yeah.
always produce, is it always happening in like circular latitudes?
Yeah, you can find pictures of like it's not just Earth either. Other planets that have their own atmosphere also have this effect. And yeah, it's always this circular. So they're coming in this direction. So I guess the ones, yeah, I
Because
don't.
they're twisting, it's just dropping them all at the same location.
Yeah, I guess so. I don't know all of the details of it, but this is the basics of the aurora borealis. So what I want to do is I want to move to Science 241. It's the electronics lab, and we'll see a little demo of some of these sorts of effects.
Are we gonna-
No, we'll